Okay, Bismillahirrahmanirrahim. Assalamualaikum. So we start our lecture on this chapter, which is we're going to talk about sensors. Strain gauge, or also alternatively known as strain gauge, is a device used to measure deformation or strain of an object. So whenever there is the object having this kind of deformations, it will produce strain. So, strain gauge was invented by Edward Simmons and Arthur C. Rooch in 1938. Okay, there are several types of strain sensors, and they use a secondary step in sensors to measure several kind of parameter such as flow, pressure, weight, and acceleration. So all these are all the examples of parameters that can be measured using the deformations of materials, which is measured as strain. Okay, the most common type of strain gauge consists of an insulating flexible backing which supports a metallic foil pattern. So this is the insulating flexible backing, and this is the metallic foil pattern. And the gauge is attached to the object by a suitable adhesive to attach it onto this material, the flexible insulating material. So as the object is deformed, the foil is deformed as well, so causing its electrical resistance to change. So whenever we apply, for example, force onto these insulated materials, and these things, since it is flexible, so it will deform. So like for example, when it is stretching, this metallic foil will also stretch. So consequently, the resistance in this material coil will be affected. Like for example, if it's elongated, the resistance will increase. Okay. So like when there is a tension, basically when you have tension, it will make the materials elongated. So due to that, the resistance increase. Why is increased? When it's elongated, what happens to the length of this metallic foil? It will increase as well. And meanwhile, the width of this metallic foil, it will decrease. If you remember the relationship between the resistance, the length, and the cross-sectional area, where the resistance is directly proportional to the length and inversely proportional to the areas of the material. So due to that, the resistance will increase when there's a tension. So this resistance change is usually measured using a Wheatstone bridge. So basically we have the sensor, and we need to have a signal conditioner, and where we want to translate, or we want to convert the change in resistance that caused by whatever things that we are measuring, for example force, whatever, and that parameters going to affect the resistance in the strain gauge, and we need to convert it into voltage output in order for us to read. Okay, so we use this Wheatstone bridge to convert the resistance change into voltage change. Okay, so this is the how it is, the strain gauge is connected into this Wheatstone bridge. Okay, this is the relationship of the resistance of metal with the length and with the area. This is the sample resistivity, basically is constant, and basically this is all the initial the sample resistance, the original sample resistance of that materials, where the resistance equals to the sample resistivity multiply with length and divide with the cross-sectional area. So if the material is stressed, so what is going to happen? There will be a positive change in length. So due to this, basically this is what we call it as a Poisson's ratio. So when there is a change in length due to the conservation of mass, so these things need to be maintained in mass and volumes. So what is going to happen is the area will change in the opposite sign as the length. So if the length is elongated, what happens to the area? It will be narrowed down. It will become narrower. It's like, for example, you have a rubber, for example, and then you stretch the rubbers. What you can see from the length, of course, is going to be elongated. But if you look at the width of the rubber, it will become like thinner and thinner. Okay, so it's because the volume will remain the same, but since you change the length, the area will change as well. So therefore, the resistance of sample will change. So the resistance, this is the new resistance. resistance. Okay, so it is directly proportional to L and inversely proportional to area. So when you increase this, when you apply stress, what you're going to do is you are going to increase the L, and also you're going to decrease the area at the same time. And if you compress it, what happens is the length will become negative. So the L naught minus delta L. Meanwhile, for the area, you're going to be increased and not plus delta A. So this is a new resistance. So you don't really have to memorize on how to derive this. So basically, you can say approximately the change in resistance is equal to the original resistance multiplied with the change in length over the original length. This is gauge factor. Basically, gauge factor is the ratio of the change in resistance with the original resistance over the strain, where strain actually is presented or defined as the ratio of the change in length over the original length. So a Wheatstone bridge is divided bridge circuit used for the measurement of static or dynamic electrical resistance. And the output voltage of the Wheatstone bridge is expressed in millivolts output per volt input. It is usually very small, the voltage output from this Wheatstone bridge. So the Wheatstone bridge circuit is also well suited for temperature compensation. So like when you apply, for example, if you apply pressure on the strain gauge, other than that, temperature of in that room where you apply this sample is probably going to affect as well the resistance, so it needs to be compensated. So this Wheatstone bridge, it can help to eliminate the temperature. So typically the rheostat arm of the bridge is in R2 in the diagram. Okay, the rheostat arm of the bridge R2 in the diagram is set as value equal to the strain gauge, so without any force applied. So R2 is equal to the resistance of the strain gauge, and the two ratio arms of the bridge R1 and R3 are set equal to each other. So why we want to have this is because of we want to satisfy the null condition. So basically, if you remember, the null condition is where R1 times R4 is equals to R2 times R3. So the 1 is multiply with the opposite of it, R1 and R4 and R2 and R3. So by having like R2 equals to R4 and R1 equals to R3, basically you at the same time you will satisfy the null conditions. Because when there is no force applied to the strain gauge, the bridge will be symmetrically balanced and the voltmeter will indicate 0 volt. This is because it is satisfying the null conditions. So as the strain gauge is either compressed or tense, its resistance will decrease or increase. The resistance in the strain gauge will increase or decrease, depend. So and it is compressed, the resistance will decrease. If it is tense, the resistance will increase. So the unbalance in these two legs of this bridge, it will produce an indication at the voltmeter. So this arrangement with a single element of the bridge changing resistance in response to the measured variable mechanical fault is known as quarter bridge circuit. So quarter bridge circuits means that you have like 3 fixed resistance 1, 2 and 3, and only one of it changing resistance. So it's 1 over 4. 1 out of 4 can change its resistance. So this quarter bridge. So an unfortunate characteristic of strain gauge is that of resistance change with temperature as well. So if the temperature change, so like for example, if you want to check or you want to measure force, but at the same time the strain gauge is affected by the temperature as well. So there is a way on how to eliminate the effect of the change in temperature onto the change in resistance. So how we going to do this is we can use a dummy strain gauge. So dummy strain gauge is placed on the same leg as the strain gauge. Okay, on the right side, for example, if you can see from this figure. So the top one in the one located at R2 is this is what you call it, a dummy, and this is the one as you apply whatever things that you want to measure. So this one that is unstressed, and the one that is stressed. Stress is the one that you use as your sensor. So by doing this, so that the both element of rheostat arms will change resistance in the same proportions when temperature changes. Okay, like if you notice the previous slide, it's mentioned that R2 and R4 needs to be equal. Meanwhile, R1 needs to be equal to with R3. they must be equal to each other when there is no force acting on it. So like when there is no force, the R4 will be unstressed as well. So but when there is a temperature, like temperature change in R4, it will change in R2 as well. So like for example, like the resistance in R4 is increased due to temperature. What happened to R2? It will increase due to the temperature as well. At the same change in resistance, so what is going to happen? It will remains the same. Okay, the R2 and R4 will remain the same even though there's an effect of temperature. So you need to make sure that, but just need to make sure that when R4 is stressed, R2 is unstressed. So basically by using this dummy, we can eliminate the effect of this. And how you want to set this as an unstressed usually is you put it as in this coordinations, like you make it in these directions like this. So whenever like there is a stress or like compressions or tensions occurs on the materials, this on the one on the left, the dummy gauge, is not going to be really affected by the elongations or compressions, but the one is with active gauge, actually the effect of the elongations is very significant if you put it this way in these directions. Okay, so when you elongate it and or you compress it, it's going to affect. So this is how you set up your active gauge, and this is how you set up your dummy gauge. Okay, one arm bridge. So this is what we call as one arm bridge. So it's like one of the arm. So the active strain gauge will be given by these equations. RA equals to R1 plus delta R. Basically, you don't really have to memorize this. I would suggest you to memorize the Wheatstone bridge equation instead. You don't really have to memorize this. This is usually this kind of equation is a simplified versions where you use the same resistance for all resistors, where in some of the cases there's a possibility that you can use a different resistance for, like for example, R1 and R3. Basically, it will be best if they are the same. R2 and R4 will be the same, but R1 and R2 is not necessarily going to be the same, and same goes to R3 and R4. So I would suggest you to just use these equations whenever you deal with Wheatstone bridge problems. And this is the way you can find the gauge factor and also the strain, the change in length. Usually the gauge factor for an ideal case, gauge factor is equals to 2. Okay, if it's not mentioned anywhere in the problems telling that how much is the gauge factor, and it asks you to find delta L or the strain, for example, the ratio of this is basically strain. So like if I ask you to find strain and it doesn't give you the gauge factor, you can just assume it equals to 2. But usually most of the time the gauge factor is given. Usually it's like 2.01 or 2.0, but you cannot just go way far away from 2. Okay, you can just estimate, like if you estimate 2.01 is still acceptable, I can still give you mark. But you just suddenly you say that GF equals to 1 or GF equals to 3, okay, this actually is totally wrong. Okay, here you have an example, same gauge with gauge factor of 2.03 and the resistance 350 ohms is used in previous figure. So the bridge resistors are R1, R2 all equals 350, and dummy gauge has 350 ohms as well. So if a strain of 1450 micrometer per meter is applied, find the bridge offset voltage if Vs equals to 10 volt. Find the relation between bridge of null voltage and strain. How much voltage results from a strain of 1 micro? Okay, so for this question, basically everything is like a lot of things, a lot of information already given here, which are the gauge factor, the resistance for all resistors, like this is the resistance for the strain gauge, this is the resistance for this R1, R2, which is the fixed resistor, and 350 ohms for the dummy gauge. So as we seen before in the previous slides, where the dummy gauge is used to eliminate the change in resistance, the readings of the change in voltage due to the change in temperature. So that means that for these configurations, the effect of the change in temperature will not affect the change in voltage. And yeah, so basically the gauge factor is given here, 2.03, resistance 350, and the strain is 1450, and the voltage supply is 10 volts. So like, okay, best way, the best thing actually, best way to start to answer the question is by first drawing the circuit itself, the Wheatstone bridge. Okay, so you have the resistance. I'm still adapting using this pen, so that's why my handwriting is a little bit very bad, ugly. So yeah, you have here VS, you have there is R1, R2, R3 and R4. Okay, so if we look at it, if you remember the previous equations mentioned that GF is equals to the ratio of the change in resistance with the original resistance and over delta L over L, which is the bottom one is equivalent to the strain. Okay, so basically strain is already given, GF already given, and also same goes to this resistance, which is R4, and in this case is 350. So basically you can rearranging these equations, you get delta R equals to gauge factor times strain times resistance. Okay, so basically from here 2.03 times 1450 micro times 350 ohms. Okay, here you get 1.03 ohms. Okay, this is the change in resistance. Okay, so you just assume that the change in delta L is positive, so where the change in resistance is positive. Okay, so we assume that the new resistance is R4 plus 1.03. So we go back to the equations of the voltage difference. So here we get this Vs, and it is R3, R1 plus R3 minus R4, the new R4. Okay, so the new R4 will be R4 plus delta R. Okay, it's the original one when there is a null condition, we don't have any delta R, so we don't have any delta V. But here this is the results of the change in resistance, so we expect there will be a change in the voltage as well. So for the bottom one is R2 plus R4 plus delta R. Okay, this is really from delta R. Okay, so here you get Vs is 10. Okay, for this one, the left one, basically they have the same value, so basically you can get that this is equals to 1/2 minus, okay, R4 plus delta R is about like 350 plus 1.03, so you can just say down 351.03 ohms plus, so 351.03 plus 350, so you get like 701.03 ohms. Okay, so the change in voltage that you expect to get due to the change in resistance here is about negative 0.0007 volt. Okay, now we are going to find the voltage, is the difference voltage from a strain of 1 micro. So basically this question is asking for sensitivity. So if you check back, actually the sensitivity is also defined as delta V equals to minus Vs over 4 times the gauge factor times the strain. Okay, actually, I didn't mention it in the slide before that this number of 4 is just for those that have only one active strain gauge. Okay, like for this case, R1 and R2, they are all actually it's R2 is here. I just realized that R2 is here and this is the dummy. Okay, the dummy. Okay, for this case, the only active resistor is R4. So if you have only if this Wheatstone bridge is a quarter bridge, you have only quarter. So if it is half bridge, meaning that there are 2 active resistors, you need to have it we call as half bridge. So the sensitivity is minus Bs over 2. So if it is a full bridge, okay, there is no number 4 here. It is minus Bsgf over strain. So that means that for half bridge and full bridge, they are more sensitive compared to a quarter bridge. So by this, you have over 4 times 2.03 times the strain. Okay, this is 1 micrometer per meter. So at the end, so what you get is 5.05 microvolt. Okay, this is 10 volt and this has no unit. So yeah, okay, so for the very tight space here. So there's your the sensitivity.